Hey everyone, welcome back to another Explainer. So today, we're doing a total engine teardown on a seriously groundbreaking piece of AI architecture. It's a framework called LLIA, which stands for Low Latency Interactive Avatars. Now, if you've ever interacted with a digital human before, you know the drill, right? There's almost always this awkward robotic pause between when you finish speaking and when the avatar finally moves its mouth to reply. Well, today, we're going to explore exactly how the researchers behind LLIA have essentially eradicated that delay. They've achieved fluid, real-time communication through some truly ingenious optimizations of diffusion models. And really, that's the ultimate question for human-computer interaction right now. Can high-fidelity AI avatars actually talk to us in real time? I mean, can we truly break the latency barrier and have a microsecond-level conversation with a lifelike AI without those sluggish, immersion-breaking pauses? Because, it's one thing to generate a hyper-realistic video of a person talking offline, like where a computer can just churn away for hours. It is an entirely different beast to generate those frames on the fly, microsecond by microsecond, in direct response to your voice. To understand how LLIA pulls this off, we're going to follow this architectural roadmap. We'll start with the avatar latency problem, then look at variable length video generation, accelerating the diffusion process, pipeline parallelism in action, interactive and expressive avatars, and finally, the real-time future. Okay, let's dive right into this. Section 1, the avatar latency problem. So, for a while now, developers have been caught in this super frustrating tug-of-war. On one side, we have GAN-based models. Think of these as your fast, scrappy workers. They hit real-time efficiency pretty easily. The problem? Well, they kind of lack that final layer of visual realism and fine-grained expressiveness. The avatar usually ends up looking a bit flat or just unnatural. On the other side, we have traditional diffusion models. These are the meticulous artists of the AI world. They generate these incredibly high-fidelity, hyper-realistic portraits. But because they work by iteratively removing noise from an image step by step by step, they demand massive computational power. They're just way too slow for a real-time conversation. So LLIA's mission was basically to use that beautiful, high-fidelity diffusion model as the renderer, but somehow hack its process to be as lightning fast as a GAN.
Which brings us to Section 2, variable length video generation.
Let's see how the team built a brilliant solution for a really tricky problem. When you speak to an avatar, you want it to react instantly, right? To do that, the system needs to generate a super short minimum length video clip so it can get its mouth moving immediately. But here's the catch. Diffusion models historically hate this. If you ask them to generate clip lengths they weren't explicitly trained on, errors start accumulating, and the visual content literally collapses into a weird mess of pixels. So the LLIA team designed this dynamic training strategy. Step 1. They train the model on fixed frame lengths, say 12 frames at a time, so it learns exactly how lips and audio sync up. Then step 2. Once it's smart enough, they take the training wheels off. They transition to dynamic frame lengths during the later stages of training, forcing the model to handle unpredictability. Because of this clever trick, in step 3, during actual use, the system can fire off a tiny 4-frame clip for an immediate zero-delay response, and then seamlessly switch back to generating those longer 12-frame clips to keep the visual quality incredibly high. Moving on to Section 3, accelerating the diffusion process. To actually generate these frames instantly, the researchers sidestep the heavy traditional diffusion process entirely. They use something called consistency models. Normally, a diffusion model takes dozens of iterative mathematical steps to denoise an image. A consistency model, on the other hand, is a specialized training strategy that essentially forces the AI to learn a massive shortcut. It constructs self-consistency in the latent space. Now, what that actually means is the model learns to map the noise directly to the final image in just 2 to 4 steps instead of, say, 50. The LLIA team took pre-trained weights and trained this consistency model specifically for an audio image-to-video task. They even threw in a customized discriminator to make absolutely sure the lip sync and the character's identity stayed perfectly sharp, even with these massive mathematical shortcuts. And the result of combining that variable length trick, consistency models, and another technique called INT8 model quantization, which basically shrinks the math precision so it runs faster, is this staggering number right here, 140 milliseconds. That is the initial video generation response latency at a 384 by 384 resolution. To put that into perspective, the average blink of a human eye takes about 300 milliseconds. This AI avatar can hear your voice, process it, and begin animating its visual response in less than half a blink of an eye. Absolutely wild. Next up, Section 4, Pipeline Parallelism in Action. Now, this is where a brilliant engineering hack called pipeline parallelism comes in to keep things running continuously. Think of it like a highly efficient factory assembly line. In an unoptimized model, request 1 would go through the unit module, then the VAE module, and request 2 would just have to wait patiently in line until request 1 was totally finished. But with LLI, execution time is effectively masked by overlapping these processes. So while the VAE decoder is finalizing the visual pixels for request 1, the heavy lifting unit module is already concurrently processing request 2. No module is ever sitting around idle. They are constantly working in parallel, absolutely maximizing the hardware's throughput. Because of this pipeline parallelism, the system doesn't just respond quickly, it streams beautifully. On a single, commercially available RTX 4090D GPU, Elia achieves a breathtaking 78 frames per second at a 384 by 384 resolution. Even if you bump that up to a crisper 512 by 512 resolution, it still sustains 45 frames per second. It easily clears the threshold for smooth, real-time interactive video, and, the best part, you don't need a massive server farm to run it. Let's look at what this enables in Section 5, Interactive and Expressive Avatars. And this brilliantly illustrates what all that unprecedented speed actually enables for the user experience. To make the avatar feel truly alive, the system actively extracts acoustic features from your live audio input to dictate its state in real time. It's analyzing the silences, the inflections, and the volume of your voice to understand the context of the conversation. This allows the avatar to behave naturally, even when it isn't the one actively talking. The researchers achieved this incredibly natural behavior by embedding 3 distinct conversational class labels into the model. When the avatar has the floor, it's in the speaking state. But what happens during those microsecond gaps when you are talking? Instead of freezing up like some creepy mannequin, the model detects your voice and shifts the avatar into the listening state. This triggers encouraging nonverbal cues like nodding or smiling to show it's engaged. And if there's total silence, it seamlessly shifts into an idle state, where it maintains a stationary posture and just passively waits for instructions. It is constantly reading the acoustic room, so to speak. So the crucial point here is that we want a genuinely lifelike avatar, not a static puppet. A major flaw in older models is that when you feed them a reference image of a face, the AI tends to just blindly copy whatever expression was frozen in that photograph. Like if the person was frowning in the source photo, the avatar frowns through the whole video. LLIAA fixes this by introducing explicit facial expression control. They run the reference image through a pre-trained portrait animation model first, specifically to alter the facial expression. This effectively disentangles the person's appearance, their identity, from their expression. So the system can seamlessly force a smile, a furrowed brow, or really any emotion onto the face before it even hits the reference net and generates the video, resulting in a vastly more expressive digital agent. Which brings us to our final takeaway. Section 6, the real-time future. As the researchers themselves put it, this research opens up new possibilities and perspectives for leveraging diffusion models in time-sensitive, user-driven multimedia generation scenarios. What they've essentially done is bridge that seemingly impossible gap between the cinematic, high-fidelity quality of a diffusion model and the hyper-fast, low-latency operational demands of real-time software. They prove that you really don't have to choose between visual realism and speed anymore. With the right training paradigms and clever pipeline optimizations, you can absolutely have both. Which leaves us looking squarely at a rapidly approaching reality. The technology to render a photorealistic human face, lock eyes with you, listen to your words, nod along, and respond in less than the blink of an eye is no longer theoretical. It's actually here. So with the latency barrier finally broken, what will your first real-time conversation with a lifelike AI look like? Will it be a digital tutor, a customer service agent, or something else entirely? It is a fascinating future to ponder. Thanks so much for joining me on this explainer. Keep learning, and I'll catch you next time.